Hello, I'm Terrence McNally, and welcome to today's podcast. This week, we're going to talk about space exploration, both outer and inner. Rob Manning is chief engineer of the Mars Science Laboratory, that's at JPL and NASA. His previous work, he's been with this kind of work for years now, and I'm going to let him tell you kind of how he got to what he's doing today. Rob Manning, welcome.
Thank you, Terrence. This is fantastic. I'm very excited to be here.
Very good. Could you tell us what path does one follow to become chief engineer of the Mars Science Laboratory and be willing, because I like people to get a sense for the people besides the ideas and the work that we talk about, be willing to talk about mentors or moments of decision along the way?
Well, that's a great question. It's funny. There really is no one path. I think the best thing to do for anyone who is curious about the world, and I think anyone who is curious, learn as much as you can about as many different things as you can. And in my case, I was very lucky to study both math, physics, and engineering and in school, and I was able to apply that. And more importantly, I learned about what I need to learn on the job. I tried different paths. I didn't stay stuck in one direction. I learned from great mentors and great people and some fantastic stories. I mean, the wonderful thing about here at the Jet Propulsion Laboratory in Pasadena is that the people here have been doing this since the 50s, and that experience is handed down from one generation to the next in the form of stories and experiences and ideas and lessons. And to me, it's just been a fantastic adventure. I'm so lucky to be here.
Oh, thank you. You know, one of the things that, of course, I seldom think about it. As you were saying that, I heard it. Jet Propulsion Laboratories, to think that something that originally had the newfangled name of jet propulsion is now dealing with trips to Mars.
That's
you
right.
can see how far we've come.
Now, we still do a little bit of jet propulsion, but not much. In fact, the skills you need to do this kind of thing are really amazing, from people who really are experts at rockets to people who are software designers, people who can design mechanical systems like wheels and robotics, people who are good at thermal design, people who understand material science, and even people who know how to sew fabric. I mean, it's amazing how many different skills you need to have in order to pull these kinds of things off.
Now, one thing I want to hear is, when you were a child, when you were looking up at the sky or working on a project for third grade or fifth grade, was there some moment where you said, I want to have something to do with the space program?
Oh yeah, I have to say yes. When I was growing up, I was growing up in the 60s and 70s, and right at the time when the Apollo program was going on, humans were going into space for the first time. And as a kid growing up and reading about it in National Geographic, Time magazine, and just following it on the radio, it was just unbelievable to me that people were actually doing these things. And I have to admit, like almost all young boys at that time, we all imagined ourselves being astronauts.
Right.
So that inspired me to read books about science fiction, read about what a scientist is and what people study to become an engineer. In fact, I really didn't even know what an engineer was until late into high school. I realized that there were people out there, and you could take these classes and learn about this stuff almost anywhere in the world, and it's really fantastic. And there are people all over who really can study this stuff, even from their own homes with the World Wide Web. You can really get at this information now. You don't even have to travel to other big cities to learn this like you had to do when I was growing up.
And I know that MIT and some of the other elite science institutions are some of the leaders also in putting a lot of their classes online for free.
That's right. They're doing it's really it's stunning what you can actually get. And so for people who have genuine curiosity and who are interested in science and math, or just odd, goofy things like what we're doing tonight, you can learn about it. You can go online and find out about it and learn some of the physics and actually kind of live vicariously through our work. It's really fun.
Yeah, let me just share with you that my family moved to Merritt Island, Florida, when I was entering my junior year in high school. So my junior and senior years living in Merritt Island, you would hear windows rattle. And whether you were in school or at home, everyone would rush to the windows or rush outside, and we'd watch another rocket take off. At that point, they were going, it seemed, every 4 to 6 weeks. My summer jobs after my senior year in high school, my freshman year in college, one was at Patrick Air Force Base, one was at Cape Canaveral. It was really an amazing feeling. So let me ask you, let me tell people first, I'm speaking with Rob Manning. Rob is Chief Engineer of the Mars Science Laboratory, which is the name for the Rover Curiosity mission. And in just over 9 hours, the Rover Curiosity is scheduled to land on our neighbor planet. To learn more, go to nasa.gov and definitely check out the video, 7 Minutes of Terror, which is it explains a great deal, and it's also just wonderfully made. What is your job? What does it mean to be Chief Engineer, Mars Science Laboratory?
Well, Chief Engineer, it's a great title, and I love that title. But what it really means is making sure that all this fantastic, amazingly talented group of people know what to do and how to work together. And if there's any problems that they can't solve within their area, that I can come along and bring them together to help do problem solving. Whether it's finding a new solution for a new design, whether it's that's not working, or if it's a software bug that we need to go fix and figure out whether it's really a hardware problem or a software problem, I'm in there with the team and bringing them together to make sure that the problem is licked and we understand it and we know what to do to go forward.
It goes back again to that thing you said at first, which is that rather than being the expert on the head of the needle, sort of, you grew up a generalist, and so as chief engineer, that comes into play, doesn't it?
It really does. I've been very fortunate to have lots of very specialist career paths in the past that help me understand just how much work has to be done at the lowest levels to get something like this built. But I work with people whose skills far surpass mine, and who are very so good at what they do, but they can't necessarily communicate with another group of people who may not even be familiar with that discipline. So my job really is to be a translator between different kinds of disciplines.
Now, there was an article in the LA Times yesterday that included this line. I'm going to read it. Quote, regardless of whether the Curiosity rover lands safely on Mars on Sunday night, Manning can say, with a clear conscience, he did his best to ruin it. Tell us about that, and what did you try?
Well, I wasn't trying to ruin the actual mission. The role I had, we have, as part of our testing, we test the real hardware, the real software as much as we can, and the equipment that's flying to Mars, we actually have duplicates of here in Pasadena, and this equipment allows us to actually do the whole mission of practicing the whole thing. We can fake out, produce virtually a virtual world around our duplicate equipment, and make it think that it's really flying to Mars and landing on Mars and doing science. But more than that, we can hook that up and make the operations team, watch the vehicle and control the vehicle exactly as if it was on Mars. So we've done a lot of these tests. We call them operations readiness tests. So we've done many of them. We do them under normal circumstances, but once in a while we'll pick a certain set of tests to do where we want things to go wrong. And what we're going to test is the ability of the team to figure out how to recover when bad things happen. Because it's amazing, and in fact, this really goes back to the whole history of space exploration. Bad things do happen.
Well, I read a note in the LA Times editorial this morning, I think, that said more than 2/3 of previous Mars landing attempts failed.
That's exactly right. But even the ones that succeed,
right,
like Spirit and Opportunity rovers and Mars Pathfinder or Phoenix, all these missions, we've had things go wrong, and it's up to the team to fix it and figure out how to work around those problems. But to do that, the people themselves have to be experienced in how to do that kind of problem solving and how to see the rover through the eyes of this very narrow radio link that travels millions of miles across the solar system. So my job at this operations readiness test was to throw bad things at them to see how well the team could recover.
That's very good. Now, there's been a great deal of emphasis, I did it myself in the introduction, on the difficulty of the landing. NASA and JPL, as I said, have released that wonderful video, 7 Minutes of Terror, which I highly recommend. Go to nasa.gov and check that out. Now, that's obviously, emphasizing the difficulty of landing is obviously good PR in terms of attracting interest, but it's also the reality. How do you, describe that challenge?
Well, this has been a challenge for all of our Mars landings. This is number 7 successful mission. We hope it'll be the 7th successful mission on the surface of Mars since the 1970s. But each time you land on Mars, it turns out it's really, really tough. Mars is actually it's not a very friendly planet to land on. It turns out it has an atmosphere, but the atmosphere is only 1/100th the density of Earth's. So you can use the atmosphere like you do when you land on Earth with a heat shield and a parachute. But the trouble is, it's still so thin that you're still going toward the ground at 200 miles an hour. So
it's enough atmosphere to give you trouble, but not enough to slow you down.
Right. So you have to be. So if you were landing on the moon, you don't have an atmosphere at all. So you can just use your rockets all the way to the ground, like the Apollo astronauts did. But what the Mars is a strange combination. It's at near the bottom. The air is still so thin that you really have to go back and use a propulsive-like landing system. So this vehicle has to, like a transformer, has to transform itself from an interplanetary vehicle, a hypersonic flying aircraft, a parachutist, and then finally a jetpack helicopter pilot lowering itself to the ground. And that transformation has to happen all by itself because we can't control it from here on Earth. Mars is too far away. It's 14 minutes for a radio signal from Mars to get to Earth and back again, and another 14 minutes to get back. So there's no way we can joystick it from here on Earth. It all has to be programmed, and that precision landing has to be done by the software on board. So that's what makes it so tough. On top of that, we have another little difficulty in that we really can't test this thing on Earth because of the differences between the gravity and the density of the atmosphere. It's not possible to test this whole system here on Earth without breaking to lots of little tiny pieces, and that's what makes this thing so difficult.
So, in other words, as I've read up, it's 76 pyrotechnic devices, 500,000 lines of code, and 0 margin of error, and this will be the first time all of the pieces have come together.
Right.
Now, and the other thing that I love is that it takes 14 minutes for a signal to reach here, but only 7 minutes from the time that the vehicle hits the atmosphere of Mars to the time it has to land. So
right.
When we get a signal that it's hit the atmosphere, it's already 7 minutes since it either failed or succeeded in landing.
Right.
I love that.
Right. It's a bit like watching the Olympics delayed.
Yeah, only a little more riding on it in terms of billions, etc. But you said they've all been difficult landings, but this one you needed to devise a new landing system. The ones that you used in the last two didn't work because?
Well, we used, if you remember, Mars Pathfinder we pioneered landing on Mars using airbags and solid rockets. It's a good combination. Solid rockets do a good job of slowing you down, sort of, but you still have more speed left, so you need to have airbags. In the case of Spirit and Opportunity, we used the same technique, and those little rovers bounced over the surface of Mars. They rolled a little over half a kilometer, bouncing 8 meters in the air, and finally rolling to a stop. Now, in the development of those airbags for Mars Exploration Rover, we had really had a lot of trouble getting those airbags to work with that heavy lander. And it was because of the shape of the rocks, the velocity, how the airbags would tear. And we were very nervous that we could not make a larger lander system using that same trick unless we really control the velocities a lot more and make sure that touchdown.
And how much larger is Curiosity than the previous?
Well, This is 5 times heavier and at least twice the diameter, so it's a lot bigger. And it's a lot bigger. We don't like bigger just for the sake of bigger, but this vehicle had to be bigger in order to be a roving geochemist. Spirit and Opportunity were roving geologists. You don't need to bring a lot of equipment to do a roving geology job. But if you're going to go to Mars and you want to do chemical analysis or mineralogical analysis, you need to bring laboratories with you, and that made this vehicle a lot bigger. So we said, listen, if we're going to bring science lab, we need to come up with a new way to land this thing because airbags aren't going to work. We had actually tried looking the traditional way, putting a lander underneath the rover and have the rover land on top. But it turned out with the heavier rover, it made that job all that much more difficult. So we came up back in 2000. Actually, we came up with the idea of flipping it upside down, putting the jetpack on the roof, and then and like we did with Spirit and Opportunity, lower it down on a rope and put the rockets up on high. And that's, instead of using solid rockets, we would use very precision-controlled liquid rockets to control the speed. So it's just like Pathfinder and Spirit and Opportunity, except that it's the velocity of touchdown is so low, you don't need airbags. You can land right on your wheels.
Yeah, but to do that, you added a couple of steps that are really, really intricate. So that's the thing. To be large enough to do what it needs to do, needed to come up with a new way to land. How did you pick the landing spot?
Well, the landing spot, this is the most exciting thing about this project. One of the things that our previous missions, when these vehicles hit the top of the atmosphere, although we were pretty good at aiming for the spot above the atmosphere from Earth, once it got the atmosphere uncertainty, our ability to predict what the density of the atmosphere is going to be is not that great because Mars has incredible changes of its atmosphere over the course of days and weeks. So when we land, we don't know where we're going to land. We're aiming on these previous missions. We were aiming for a spot the size of Southern California. Now we can land at a spot somewhere between downtown LA and Santa Monica, right? We can a 10-mile stretch about 5 miles across, and we can be much more precise. And the reason we can be more precise is because for the first time ever, we're going to fly this vehicle like an airplane. While we're flying through the atmosphere, before the parachute opens up, it looks like a space capsule, but like the human landing systems from the 60s, and this vehicle will actually steer its way and use lift to guide itself to this much smaller landing footprint. Once we found that we can land with a smaller footprint with this new technology at Mars, we realized that we could go to much more interesting places, and the scientists have been extraordinarily excited about that capability because now you can land right next to really cool places. All the other places we've landed were like Oklahoma with bumps on it. And the reason for that is because people like me said to the scientists, no, you can't land near that mountain. We will crash.
Right.
We can't do that. So what we did was, by making the landing area small, the scientists could find flat landing areas in valleys right next to their most interesting topographic features. And that's what we're doing. We're landing at the base of this fantastic mountain, Mount Sharp. It's 3 miles high. It's higher than Mount Rainier. It's in the middle of this big crater called Gale Crater. So this mountain is smack in the middle, and it has this huge mountainous rim that we're landing. So we're landing between the rim and the center of the crater where this mountain is, in a nice flat spot. And the great thing about landing at this mountain is that this mountain is a layer cake of time. The bottom of the mountain has some of the oldest rock on the surface of Mars. The upper layers have the most youngest rock and layers on the surface of Mars. We can, by climbing up slowly from the base of the mountain, we'll be able to peer back into the earliest moments of time of Mars, when we think Mars may have possibly have been a warmer, wetter place, much like Earth was at the same time 3.5 billion years ago.
We only have about 4.5 minutes left. Rob, what I want you to do is tell us what the purpose of this is, but before you do, 2 quick, very technical questions, or maybe 3. How far from the landing site will it rove? How fast does it rove? How steep an incline can it deal with? And how long do you expect it to last? Those are the quickies, and then I want you to take the rest of the time to tell me what you're studying and how you're doing it.
Well, what we're going to do is we're going to land in this ellipse. This ellipse is about 20 by 7 kilometers, and it's right at the bottom of this at the foot of this mountain. What we'll do is we'll drive out of our ellipse. We'll be able to drive at least 20 to 30 kilometers up. We don't plan to go to the very top of the mountain. That's just too much climbing. But the really interesting stuff is down at the very bottom. So that will take us 2 Earth years. That's 1 Mars year. Mars goes around the sun once for every 2 times the Earth goes around, and this will allow us to, over this year, to traverse that distance and very carefully explore those layers of the bottom of Mount Sharp. And so, but this vehicle, like Spirit and Opportunity, doesn't move very fast.
Right.
This is not.
It's a mile and a half an hour, something like that.
Yes.
Yeah.
Yes. No, actually, much less than that.
Oh.
Much less than that. It actually on a good day we can get 2 football fields in an hour.
Oh, okay. So, I get it. Yeah. So that's like a mile and a half a day. But it's going to be climbing up this mountain, right?
Yes.
That's so amazing. Okay, now the research. You're looking for because Viking in 76, I'm doing this quickly, Viking in 76 said there's no sign of life on Mars. We kind of gave up on it. But since then, we've discovered that it looks like there is water, has been water, may still be water. Water's one of the elements of life. Carbon molecules and energy are the other two. You're looking for carbon molecules, right?
It would be great if we could find carbon molecules, yes.
And so one of the things that really excites me is the laser that shoots at things and then turns them into plasma, and then you analyze what's in the plasma?
Yes. This is an instrument called a ChemCam, which is developed in France, and it's a fantastic instrument to allow us to understand the mineralogy of rocks about 20 meters away. So instead of having to drive up to every rock and sniff each one, we can actually shoot them from a distance, and the flash of light is converted into its spectral colors, which will allow us to understand the mineralogy of that rock that we're burning up.
That's just amazing. And so with that, so again, what you said is that mountain you believe has the layers
right.
of the history of Mars.
Exactly.
And so as it climbs up, it samples something here and tests it, samples something here, samples something there, correct?
Correct. And so the main idea here is this: we've known that water has been on Mars, is still on Mars in the form of ice. Mars is a very cold place, and still very dry, and we believe the surface is in fact sterile because of the ultraviolet light and the absence of an ozone layer. So what we can find out though is back 3.5 billion years ago, was the climate on Mars conducive for the formation and sustaining presence of life? And that history, that climate, is stored in the geological record of each layer. And we can find out exactly whether or not the climate of Mars may have been conducive for living cells to survive, single-cell organisms. That would be fantastic.
And one of the things I'm just going to add, and then I'm going to sum this up, the earliest history of Mars is better preserved than it is on Earth. And so we have a chance to gain insight into the development of our own planet through studying this ancient history of Mars, correct?
Exactly. In fact, it's even more exciting than that because if we find evidence of past carbon-based organic chemistry on Mars, if we could find out that maybe life was there at one time, it may still be there today. And it may very well be, as we've discovered with fascinating rocks like ALH 84001 from Antarctica, it's possible that rocks travel back and forth carrying life. And it's very possible that life on Mars may have come from Earth or vice versa.
Very good. The rover Curiosity is scheduled to land about 10:30 p.m. Pacific, 1:30 a.m. Eastern. To learn more, go to NASA.gov. Check out the video, 7 Minutes of Terror. Thank you, Rob Manning. Normally, I'd say I wish you and NASA and JPL all the luck in the world. But in this case, I wish you all the luck in the solar system.
Thank you.
Keep up the good work.